Welcome, Algebra 2 students, to our lesson on piecewise functions. So now we will finally learn how to sketch the graph of these type of functions as well as write their equation. So my name is Mrs. Lasner and I will be going through this lesson with you today. So before we begin with writing the equations and graphing, let's just take a look back at something we had learned together in section 1.2, and that was how to evaluate a piecewise function. That's when we were first introduced to this interesting notation. But if you recall, these pieces here were the actual equations. And we also learned that f of x is just another name for y. And so sometimes the y value equals -7. It would equal that when x's were less than -2. At other times it equaled x plus 4. Those were for x's between -2 and 3. And then even other times it would equal 2x when x was greater than 3. So depending on what the domain restriction was, the way we determined the output changed. So just as a quick review, let's kind of evaluate this function at different x's. So in number 1 here we have an x value of 5, which just as a review, that's what it means. When the number's in the parenthesis, that's the x value, and then we're trying to find the y value. So with a piecewise function, you have to kind of figure out which domain restriction that belongs to. And since this is a negative number that's less than -2, it would match that domain restriction, which means it would go along with the y value of -7. So we would say this: f of -5 is equal to -7 because -5 belongs to that first domain restriction. It's less than -2. Then for the second piece, we have an x value of 3, which would kind of go along right here where it says x is less than or equal to 3. So that matches with this equation. So when I'm trying to evaluate f of 3, I would have to plug in 3 for this x in here, because f of a number between -2 and 3 is evaluated by adding 4 to it. So 3 plus 4 is 7. So f of 3 equals 7. Then for finding f of -2, that would correspond with this part here, right? X is equal to -2, so that again goes with that middle piece of x plus 4. So we would plug -2 in for x in that equation to get 2. So f of -2 would be 2. So for both parts, for both numbers 2 and 3, we were using the middle piece because they both belonged within that inequality. Why don't you guys try 4 and 5? So for number 4, the output when x is 2 is 6. This is because 2 is a number that would fall within that second domain restriction. It's between -2 and 3. So then that means I would plug it into this middle piece, x plus 4, except I plug in 2 for x. So I get 2 plus 4, which is 6. For f of 0, again, I would use the middle because 0 is also a number between -2 and 3. So it fits within this middle domain restriction. And so again, I would use that middle piece to determine f of 0 by doing x plus 4, except 0 for x. So 0 plus 4 is 4. So my answers were 6 and 4. So now that we've reviewed a little bit of evaluating, let's go ahead and start looking at how these functions piece together. So the following graph here is called a piecewise function because it is defined by 2 or more different equations applied to different parts of the function's domain. Each of these equations turn into a piece on the graph. And I hope you can see here that this graph has 3 pieces. And I'm going to think of this one here as piece number 1. The middle horizontal line is piece number 2, and then this very steep line on the right as piece number 3. So it helps, if we're going to write an equation for this, which is what we're going to do in number 10, it helps for us to get the slope of each of the pieces. So first of all, I hope you can recognize each of these pieces are lines. They are linear. And so to write equations of lines, we need their slopes and we need a point on each line. So we're going to use that to get our equations. So let's go ahead and find the slope of each piece. So for the first piece, and the way we read a slope off of a graph is by doing rise over run. Let me just move this out of the way for a sec so we can count the slope. So if I take this point here and maybe use this point here, I can see that it goes up 3 and over 3. So it has a rise of 3 and a run of 3. So really, that's a slope of 1. So you could also look at it that way, from point to point. In this case, you can see it goes up 1 and over 1, up 1, over 1, up 1, over 1. So I can see that the line, the first piece has a slope of 1. For the second piece, because it's a horizontal line, it's flat, you could think of it as it doesn't have rise, it only has run. So it has a slope of 0 because rise over run would be 0 over a number. So for the second piece, we just say that the slope is 0 because it's horizontal. And then for the third piece, again, we're going to do rise over run. So I'm just going to try to find another obvious point. It looks like this one's kind of going right on the corner, and then same there and same there. So based on these points, it looks like it's going down 2 and over 1 each time. Down 2 and over 1. So I'm going to say that the slope is equal to -2 over 1, or just simplified -2. So then let's get a point, an easy point for each piece. So for the first piece, I'm going to just use this solid one here that was at -6, +1. There's my ordered pair. For the second piece, maybe I'll use the y-intercept. In fact, whenever I'm able to, like whenever I can see the y-intercept easily, I'm going to use that as my ordered pair. And then for the third piece, maybe I'll use this point up here that was at 4, 6. So we use this point here, -6, 1, that point there, 0, 2, and this point there, 4, 6. Okay, so now we're going to try to write the full equation for each piece. And just a little review from the 2.3 video. It's going to be helpful for us to use this HK version of a line. It's basically a form of point slope where M is your slope and HK, when you put it together, is your ordered pair, your point. If possible, the other nice version of a line to use if we have the y-intercept is what's called slope-intercept form, because again, you would need to know your slope. And then B is your y-intercept. So if we know what the y-intercept is, we can just use slope-intercept form. If we don't know the y-intercept, but we know another point, we can use this HK form of a line. It's a very helpful tool. So let's go ahead and get the equation for the first piece. And because in that instance, I did not know the y-intercept, I'm going to use this point as my HK. So I'm going to say M is 1 and HK is -6, 1. So if I want to put that together with this HK version of an equation, it would kind of look like this. So I would have y equals 1 times x minus h, which would be the x coordinate, which is -6, plus k, which would be the y coordinate, which in this case is 1. So when I simplify that a little bit, I get y equals x plus 6. And since that was just a 1 right there, I don't really need these parentheses. And then I have to add 1, so then I get this. Y is equal to x plus 7. That's the equation for this first piece right here. So I'm going to write that down here. Y equals x plus 7. And then I'm going to erase that right now to find the equation for our second and third piece. For our second piece, we see that the line is horizontal, so the slope is 0. So let's say and because I knew the y-intercept for that piece, I'm going to go ahead and use slope-intercept form. And so when I do that, I plug in 0 for my slope, and then I have 2 as my y-intercept. The x disappears out of the equation because notice in both of these, the HK form and the slope-intercept form, the m is getting multiplied to x. So if m is 0, it's going to take the x away. And so my equation for the second piece is just y equals 2. So that's the equation for the second piece. And then for the third piece, again, I'm going to use the HK form because I don't know the y-intercept, but I do have an HK. So my slope for that one is -2, and my HK for that one is 4, 6. So plugging it all in, I get y is equal to the slope, -2, times x minus the h value, which is the x, and then plus the k value, which is 6. And I'm going to just go ahead and leave it that way because it's okay to leave an equation in HK form. It wouldn't be too hard to simplify, but it's also okay to leave it like this. So I'm going to write that for our third equation. So y was equal to -2 times x plus 4, or sorry, x minus 4 plus 6. Okay, so we have piece 1, piece 2, and piece 3 all figured out because we knew the slope of each piece and we knew the ordered pair for each piece, and we have these sort of templates for linear equations that we can just plug these points and slopes into. But if I move down here to number 10, let me show you how we would use it with proper notation. Okay, proper notation. So notice number 10 is the same graph. Okay, guys, so I'm just going to take the information we found up here and write it down here as my answer. For notation, we start with this f of x, okay, and then we do equals, and then we do a large one-sided bracket. We don't close the bracket on the other end. It's just a left-hand bracket. Now remember, this f of x is the same thing as y, so you can actually call it y as well. But what I'm saying here is, when we're writing in these different equations for the first piece and the second piece and the third piece, we don't write the y equals part. We only write what y equaled, okay? Because the y equals part is already taken care of over here. So for the first piece, the y was equal to x plus 7. That's what I write in the bracket. I write what it equaled, x plus 7. But that was only true for certain x's. So if you look up here at the graph, that was only true from the x of -6 until the x of -3. So thinking back to our last unit, that would kind of look something like this. And I would include -6 and I would not include 3. It would look like this. From -6 is less than or equal to x is less than 3. I used the inequality without an equal sign for the circle that was open. And then I used the inequality with the equal sign for the circle that was closed. And notice I'm only using the x value of each of those points because that's just talking about the domain, not the range. This part right here tells us what the outputs are. So that was piece number 1. And then piece number 2 was the horizontal line. And the equation for that was y equals 2. So I don't write the y equals part because that's already taken care of right here. I just write the 2. And then I notice that that's in between 3 and 4. Sorry, -3. Whoops, I should have wrote -3 there as well. Sorry. -3 all the way to +4. So it would kind of be like this. Close circle on -3 and then open circle on 4. That's the domain for the middle. So I would do -3 is less than or equal to, include the equal sign there, x, which is less than 4. No equal sign because there was an open circle at 4. Then my third piece, that was the one that had this equation, the -2 times x minus 4 plus 6. That was the what y equaled, but don't write the y equals part because that part is taken care of right here. So it would be -2 parentheses x minus 4 plus 6. That's what the y equaled. And that was a ray, right? These two were segments. That's why they each had 2 endpoints, because they had a starting point and a stopping point. But this last one is a ray, so it only has one endpoint, and that was at the x value of 4. So and it's solid, so it's kind of like that. So then I would say x is greater than or equal to 4. I include the equal sign since there was a solid dot, and it just goes forever greater since there's like an arrow at the end, meaning it's just going to extend indefinitely to the right and going down. So this here is how we would write the equation for this function. Now we're going to try that again in number 11. So in number 11, you can see that we have 2 pieces. We'll let this one on the left be piece number 1, and this one on the right be piece number 2. And so what we're going to do for each piece first is find the slope. So why don't you guys take a look at these graphs and determine the slope for piece 1 and piece 2. So we recognize with piece number 1 that the slope, if you count rise over run, and I just used this y-intercept point and this point down here, and I counted that it goes down 3 and over 3, which would be a slope of -1. Or you can look from point to point. It looks like it's going down 1 and over 1, down 1, over 1, down 1, over 1. So it's got a rise of -1 and a run of 1. So a slope of -1. For the piece number 2, the one that's pointing up and to the right, it looks like on the graph that it has a rise of 1 and a run of 2. It looks like it's going from here up 1 and then over 2 to get to its next point. And then from there going up 1 and over 2 to get to the next point, and so on and so forth. So it looks like it has a slope of 1/2. Now for the ordered pair, since the first piece goes through the y-axis, I'm going to use that as my point. So I'm going to use the ordered pair of 0, 4 for the first piece. And then for the second piece, I'll use the given point, the one that's like easy to see from the given graph, which looks like it's at 3, 4. So I'll use that for piece number 2. Now for the domain restriction, that means like what part of the x-axis is it on? I can see for this first piece, here let me erase this part. It had an open circle right there where x is 3. So it's not including 3, but that's kind of how far it goes up to, and then it's everything to the left from there. So that would be my domain restriction. For the first piece, it would be x's that are less than 3, not equal to because of the open circle. And then for the second piece, the one on the right, it looks like it also starts at 3, but it's including 3. It has a closed circle there, and then it continues to the right. So that domain would be all of the x's that are greater than or equal to 3. I'm including the equal sign there because this piece includes the solid dot. So now what we need to do is get an equation for each of these lines using our slope and whatever point we got. So for the first piece, this one over here on the left, I'm going to use the slope-intercept form. So our m in this case is -1 and our b is 4. So this equation would be -1x plus 4 for the first piece. And then for the second piece, I'm going to use the HK form because I don't know the y-intercept, but I do know another point. We'll think of the 3 as h and the 4 as k. And then 1/2 is our m. So then I'm going to get y equals 1/2 parentheses x minus 3. So remember, because we subtract h in the HK formula, then the sign of this number is always opposite what it is in the ordered pair. So here it's +3, and so then that's why it's x minus 3 in my equation, and then plus 4. And you can go ahead and just leave your equation like that for the second piece. And we only had 2 equations for this function. So now let's go ahead and put everything together using proper notation. So when we use proper function notation for piecewise function, we usually start off with like an f of x, or sometimes we call it g of x or h of x. You're welcome to just call it f of x. We put equals, and then we put this bracket because we're going to have multiple pieces. Now remember, this f of x is telling us what y equals, so we don't need to write the y equals part of each of our equations. We just write what it equaled. So the first piece was -x plus 4 that was referring to this line here, and that occurred over the domain where x was less than 3, not including 3. So that was our domain restriction for that first piece. And then the second piece was 1/2 parentheses x minus 3 plus 4, and that was occurring for values of x that were greater than or equal to 3. So this would be our answer for number 11 when you sort of put it all together. And you know, I kind of actually like when students leave their HK form like this, because then it's really easy for me to spot a point on that line and the slope. So it's okay to leave it in this form for your answer. So what we're going to do next in number 12 and 13 is sort of put everything together to graph a full piecewise linear function. So remember, they're made up of smaller pieces, which we learned in the last video are rays and segments. So we're basically drawing rays and segments, not a full line or graph, just a portion of it. And when we are graphing the rays and segments, we sketch the boundary restriction above the graph as like a helpful tool to keep our graphs in the right spot. Then we're going to do table of values for each ray and segment and making sure we're using the boundary numbers and at least one other value to sketch. And then after we draw the pieces, we want to make sure it passes the vertical line test, because we're saying that these are functions. We're even using function notation. So these functions have to pass the vertical line test, and if they don't, then we know we did something wrong. Okay, so I'm going to go ahead and start with this first one in number 12. So in number 12, I can see that I have 3 pieces. So I think I'm going to color code them. I'm going to have the first piece will be red, the second piece will be blue, and the third piece will be green. So for the first piece, it's going to have to occur for values of x that are less than -2, not equal to. So that would be, it's going to be up here with an open circle, and it's going to go to the left from there. My second piece is going to be for values of x that are between -2 and 6, inclusive. So it's going to go from here all the way over to here. Both of those are solid because it includes both -2 and 6 in the middle. And then the last part is going to start at 6 and with open circle, not inclusive, and it's going to go to the right from there. So I should have this equation graphed in this area, the middle equation graphed in this area, and then my last equation graphed in this area. Okay, so then once we kind of figure out our domain restrictions, so for the first ray, I'm going to use my boundary point, make my little table of values, 2x plus 1. I'm going to use the boundary of -2, even though it's not included, because I need to know where to put that open circle. And so I just plug in -2 for x in here. I get -4 plus 1 is -3. So that tells me I'll have a point at -2, -3. And then I'll do one more point. I'll just pick something that's less than -2, like -3, and plug that in as well. So I get -6 plus 1 is -5. So I'm going to go ahead and plot these points, keeping in mind that this one's going to be an open circle, this one here. So I have a point at -2, -3 with an open circle, and then a point at -3, -5. And then I want to also keep in mind that this line has a slope of 2, right? The slope is always the number in front of x, and it's positive, so the line should be going up as I move toward the right. So you can also think of a slope of 2 over 1 as the same thing as -2 over -1, because a negative divided by a negative is positive. So I could do more points on this line by just going down 2 into the left 1, since it is a ray. That way we can kind of fill in the remaining points. And then there's my first piece, and it looks like it's matching the boundary restriction, so I'm feeling good about that one. Then I'm going to move over to my segment, which is between -2 and 6. So I have this equation -1/2 x plus 6. And I think I'm just going to use my 2 boundary points. My first one, oh sorry, this is +6. My first boundary point and my second boundary point. So I'll plug those into this equation. So when I do -1/2 times -2, it's going to turn positive. and it's actually going to become 1 because 2 divided by 2 is 1 plus 6 is 7. And then I'll do negative 1/2 times positive 6. I'll write it as 6 over 1 though, plus 6. Maybe I should have done that here too. Just helps us multiply those fractions together a little easier. So this is negative 2 over 1. So the negatives canceled and the 2 divided by 2 reduced to 1. So it was 1 plus 6. Here the negative won't cancel, but the 2 and the 6 will reduce and make it a 3. So the negative 3 plus 6 will be positive 3. So I have a point at negative 2, positive 7, and then at positive 6, positive 3. So I'm going to plot those points. So here's negative 2 and 7 right there. And these are solid, right, because they have the equal sign on both boundary points. So these are solid dots. And then 6, 3. And then we just want to check, is that matching a slope of negative 1/2? It should be, right? It should be matching if I go down 1 and over 2, down 1 over 2, down 1 over 2. Yes, it matched. So that's our graph for the middle part. And then for the last part is array again. We are going to use that boundary of 6. Even though it's not including 6, we still need to know where the open circle is. So we use the boundary of 6. And in this case, there's no x in the equation because the y value is always 3. Even if x was 7 or 8 or 9 or 10, the y value basically is just 3 every time. So I'm going to have, so this is interesting. I would have an open circle here. But notice how the other boundary point right here had a point at 6, 3. So I had a boundary point of 6, 3 from this segment. And then I had an open circle point at 6, 3 from this ray. So this boundary point filled in this hole. Filled in the hole. So on your graph, you don't need to have a hole at 6, 3 because the middle piece filled it in, so it should be solid. And then from there, I know I'm going to have a point at 7, 3, 8, 3, 9, 3, etc. It's basically just a horizontal line at 3. And there's an arrow there because this just said x is greater than 6, so that's like forever. So it's just going to move forever to the right. So this is our graph for number 12. Moving on to number 13, see, look, we used a different function notation. We used g of x, so we'll do that sometimes. It still means y, just like f of x does. It's just giving it a different letter name. So we'll still think of this as y equals this sometimes when x is less than 0, and then the other times y equals that. So notice I have the same boundary point, and so in this case I'm going to end up having 2 rays. I'll do the first one as red. That's a ray, and then the second one is blue. And that's also a ray. So the first one would occur to the left of 0. So I'd have an open circle, and then it's going to occur on the left side of 0. And the other ray also has an open circle at 0, but it's going to be going to the right. So notice that I don't have a value of g of 0. So notice that g of 0 does not exist. That's what I use. D and E does not exist because neither one of these had an equal sign where the 0 is. So both of these are going to be open circles. Okay, so for the first ray, I'm going to use this equation, which is in the HK form. So just kind of wanted to review that really quick. I can see by comparing this equation with the HK form, I can see that the slope of this line should be 1/3, and I can see that a point on the line should be 2, 3, because that matches what's in place for H and K. So it's just kind of nice to have that in mind, even though I'm going to graph it based off the boundary point. It's kind of nice to know like where another point and slope would be on the graph. Okay, but let me just make a table of values for this equation, and I'm going to use the boundary point of 0 to figure out where that closed or where that open circle would be. So I'm going to plug in 0 for x. And when I do, I get 1/3 times negative 2 over 1 plus 3, which is negative 2 over 3 plus 3. which is positive 2 1/3. So together that makes the point 0, 2 1/3. And then I'm going to plug in another number. Maybe I'll plug in -1 because it's less than 0, right? I need to plug in values less than 0. So I'll do 1/3 times -1 minus 2 plus 3, and then that equals 1/3 times -3 over 1 plus 3. And that equals -1 plus 3, which is 2. So I have a point, another point at -1, 2. So I'm going to plot those 2 points. So 0, 2 1/3. So I'd go up and then just about 1/3 of the way between 2 and 3. And I have an open circle. And then I have another point at -1, 2. And then maybe from that point, I can do the slope a little bit more. So I have a slope of 1/3. And so we know that we can also think of that as a slope of -1 over -3. So I can also go down 1 and to the left 3. And I'll just maybe do that a couple times to help me graph this ray. So this ray is going to look like that. Now, I'm not supposed to graph this line over here. This is the domain area for the other piece. But I just wanted to show you guys that if I did continue going up 1 over 3, it would hit this point 2, 3, right? That point would be on this line if I extended it. I'm just not going to extend it because I need to make sure it stays within its designated domain area, which is less than 0. For the blue piece, again, it's array, and I'm going to use this equation -2x plus 5. So I'm going to fit that work in over here, actually. I'm going to make a table of values for -2x plus 5. I'm going to use my boundary point of 0 and then one other point that's greater than 0. So if I plug in 0, I get 5. So that would be the y-intercept, right, of this line. But it's an open circle because I'm not including 0 in the second piece. And then if I plug in 1, I get -2 plus 5, which is 3. So I have a point at 1, 3, which makes sense because if the slope is -2, it should be going down 2 over 1. So I can maybe do that like a couple more times to get some more points and then extend this line forever. And so that's the completed answer for number 13. So the remainder of this video is actually comparing piecewise functions to systems of linear equations and inequalities. So what I'm about to graph right now is not a function. It's not a piecewise function. This is a system. Okay, not a piecewise, but a system of linear inequalities. And the reason I say inequalities is because the symbols that are being used in each of these statements are inequalities versus equations. So, and then there's two of them. There's two different linear inequalities, so we call that a system of linear inequalities, which oftentimes students will confuse piecewise functions and think that they're these because they see, oh, there's more than one part and also they're inequalities. But what we have here is different. What we have here is where you're supposed to graph the line. So we first kind of ignore the inequality and we kind of think, okay, what would the line 3x plus 2y equals 6 look like? So there's two ways we could approach this. We could just plug in some values for x to get values for y and vice versa. So I think maybe I'll do that. Maybe I'll plug in 0 for x because it's just an easy thing to do because 3 times 0 is 0 and then I get 2y equals 6. So if I divide both sides by 2, I get y equals 3. So I notice that if x is 0, y is 3. So that's 1 point on the line. I found the y-intercept. And I could find another point doing a similar thing. I could plug in 0 for y. And so 2 times 0 is 0. So I get 3x equals 6. Divide by 3, and I get x equals 2. So I notice that if I plug in 0 for y, I get 2 for x. So then I found another point. So that's one option to do when you have something like this, which is in standard form, right? This is in the ax plus by equals c form. One option is to go ahead and plug in 0 for each variable to get a point. So I can plot the point 0, 3 right here, and it's going to be a dotted line because the inequality does not have an equal sign. And then I can plug in 2, 0 and connect those points. Another thing you can do with standard form equations, another option, is to solve for y to get it into slope-intercept form. So I could subtract 3x from both sides and then divide each piece by 2. And the benefit of doing that is then you can see what the slope is. So it's nice to know what that is. That's our rise over run. So then I can use that slope. So I go down 3 over 2, but I can do that a couple more times to get a few more points on the graph. And I can also do that in the other direction. And this line is going to be dotted because it's an inequality that doesn't include the equal sign. So we draw kind of like a dashed line. Then this line right here, the y is greater than or equal to -5, if I were to write that as an equation, right, ignoring the inequality for a second, I would notice, oh, y is just a constant, -5, so that's always a horizontal line, and it's greater than or equal to, so I'm going to make a solid line versus a dashed line down here at -5. And it's just because the y value is always -5 no matter what x is. So it's just like that. Solid line along -5. Then we have to decide where to shade. So usually to decide where to shade, for the standard form equations like the first one, is I test a point to decide where to shade. So for this first one, the 3x plus 2y is less than 6, because I can't forever ignore the inequality, right? I have to come back and address the inequality, because technically this is less than 6, not equal to 6. So what I do is I pick a point and then I test it. So I'm going to pick the point 0, 0 and test it with this equation to see what's true or not true. Maybe I'll test it over here. So I'm testing the point 0, 0. So that means I plug in 0 for x and for y, and I check to see if it gives me a true statement. So 3 times 0 is 0, 2 times 0 is 0, and so then I get 0 is less than 6, and that is true. 0 is less than 6. So what that tells me is that this point is on the right side of the line. It's on the side of the line where the other solutions are. So I know that I would basically shade on this side of the line for the blue line. For the red line, I can just look at the direction of the inequality because it's in terms of y. So when y is alone, when it's like y is greater than or equal to something or less than or equal to something, then you can just look at the inequality. So I know that it's greater than or equal to -5, which tells me that I should shade above. And then the solution, you could say, is the part where the graphs, the shading, I should say, intersect. So the solution would be like in here. The part where the shaded areas of both lines intersected. This would be where the solutions are. So that's what a system of inequalities is. Notice what I just did is so very, very different from graphing a piecewise function. I mean, I'm dotting lines, I'm drawing, and also I was drawing the full line. Like I didn't stop the lines anywhere. I drew the full lines, both of them, and then I shaded. This is very different than a piecewise function. This is a system of linear inequalities. I have two inequalities with no domain restriction. So I'm drawing the full lines. And yes, the inequality part does look like the domain restriction for piecewise, but notice this is part of the actual equation, not like some separate thing telling me what the domain should be. It's like the whole equation. So that's why I know I need to shade, because the shading tells me all the points that would make this inequality true. All the ordered pairs that 3x plus 2y would be less than 6. And this one tells me all the values of y greater than -5. So that's all of these points above the line. And then where they overlap would be the solutions that make both of these inequalities true. Another thing that students tend to confuse with piecewise functions is what we call a system of linear equations. So that's what this is in number 15. This again is a system of linear equations. So now we don't have inequalities anymore. We have equal signs again. So it's equations, but there's two. So it's a system. And because there's more than one, again, students often confuse this with a piecewise function. But notice what this is missing. This doesn't have any domain restriction. No domain restriction, right? It doesn't have anything that says x should be greater than this or less than that. So we're going to graph the full lines for both of these, which is different than a piecewise function. So first I'm going to sketch the graph of y equals 3 times x plus 1 minus 2. So again, this is in the HK form of a line. So I can say that the slope is 3, and then matching up h and k, I can say that that is equal to -1 comma -2, because again, the h coordinate in the point is always the opposite sign from what you see in the equation. So I'm going to go ahead and plot that point. So -1 comma -2. And then I'm going to go ahead and do the slope of 3. So I'm going to go up 3 and over 1. Up 3 and over 1. Up 3 and over 1. And I can go backwards a little bit too. Down 3 and left 1. Down 3 and left 1. And so on. And I graph the full line. I'm not graphing a ray or a segment. I'm graphing the full line because there's no domain restriction. Okay, so this is not a piecewise function. This is a system of linear equations where you have more than one line and you're trying to find where they intersect. That's what's happening in number 15. So then I'm going to graph the second one, this guy right here. The y minus 3x is equal to 7. Now this one is like nicely set up where if I just add 3x to the other side, I get something that's in slope-intercept form. So I think I'm just going to do that for this one because, let's face it, slope-intercept form is like the best, right? It's so nice. And there was like no fractions or anything, so it's like, this is like a really nice one. So I can see that my slope is going to be 3 just based on the fact that that's in front of x, and my y-intercept is going to be 7 just based on the fact that that's the number being added to 3x. So then I can graph the y-intercept of 7. And then from there, I have another slope of 3. So it goes up 3, 1, 2, 3 over 1, and then 1, 2, 3 over 1, 1, 2, 3 over 1, because I can also make the slope go in the negative direction too. And again, I graph the full line because this is not a piecewise, this is a system. Actually, this is a unique system. So this is a system of parallel lines. This is the only kind of system that doesn't have any solution because they're like train tracks. They're never going to intersect because they both of these lines had a slope of 3. But notice how I graphed the full line for each. I'm not trying to just put these together as a single function. I'm saying these are two separate functions and I'm trying to find where they intersect, if they intersect. It's different than a piecewise function. So let's keep that straight. When we're doing piecewise functions, we're not graphing the whole line. And we are not shading anything. So here's what I want you to write for the summary part. If you are given a piecewise function, okay, so for piecewise functions, what you will notice is that you only have pieces, not full lines. Okay, so it's only pieces, it's rays or segments. So that's the first thing. And then there's no shading. Okay, no shading because the equations are equations, right? It's f of x equals like different things. So that equal sign means no shading. And then it will have domain restrictions, right? You will see inequalities, but they will be related to x. So you'll see like x is greater than some number, or maybe it's in between two numbers. So the only inequalities will be related to x because that'll be talking about the domain. That's piecewise. Now, if you have a system of inequalities, like we did in number 14, if it's a system of inequalities, then you're going to have full lines where maybe some are dotted. So they could be dotted or solid, dashed or solid, however you want to call that. And they're not equations. There's no equal sign. So you won't see an equal sign in the equations at all. You won't have one at all. They're just all inequalities. And you will have shading on those graphs, right? Because of the inequalities, those graphs will have shading, and they'll be full lines, not segments, right? And the inequalities will be related to the actual things you're graphing, right? Look at this. In number 14, there was no equal sign anywhere in sight, right? It was just all inequalities. So when you have something like that, or everything has an inequality and there's literally no equal sign, that's a system of inequalities. And then the last thing we saw was if you have like a system of equations. Of course, we did linear equations, but this would be true for any equation. System of equations is there's going to be no inequality signs, okay, at all. No inequality signs, and you're graphing full lines, not rays and segments. You're graphing full lines, and you're looking for points of intersection. You're not graphing like one function. You're graphing like full functions, and you're looking for where they intersect. You're thinking of them as separate functions and trying to find where they intersect. It's different than piecing rays and segments together to form one function. And then these have no shading. So no shading on a system of equations, only on a system of inequalities. And you also will notice they don't have any domain restrictions, right? So as soon as you see something and you don't see any domain restrictions, you don't see anything like this, like x is less than that, or between these numbers, you know that's not a piecewise function, that's a system. So don't confuse piecewise functions with things that look like this, multiple equations with no domain restrictions, or things that look like this, multiple inequalities, where there's no equation, only inequalities. So that concludes this video, and we will see you in class. Thank you. Bye.